I'd like to provide you with an overview of the results from GC2, and this is really work that I did collaboratively with Shuai Liu at UCSD. So really, I'm speaking for both of us. So just a few operational details on what we did and how we did it. So Shuai and I independently evaluated all of the submissions and then compared our results for consistency. This was great because there were a couple of places where we had done things a little differently, but we arrived at the same conclusions and our results were 100% consistent. For those of you who were part of the first Grand Challenge, you'll remember that there were a number of issues that made it very difficult to evaluate some of the submissions, particularly in the pose prediction part, because things were submitted as PDB files, and it was difficult to even determine in some cases where the ligand was and where the protein was in the PDB files. So Grand Challenge 2, we used mol files for the submissions, and that made things a whole lot easier. There still were a few challenges in evaluating the pose predictions, primarily because in about a third of the submissions, either bond orders were absent in the poses or the bond orders were incorrect in the poses. So simply trying to compare the RMS of one molecule with the other was difficult because they were actually different molecules. But Shuai and I actually worked around this in two different ways. So Shuai did a maximum common substructure search of the submitted molecule versus the crystallographic ligand. And that maximum common subgraph superposition didn't consider bond order. I did the same thing, but I just did a substructure search that didn't consider bond order. Again, my results and Shuai's were 100% consistent. So I think that we were able to work around this. Next time around, we'll probably put some additional checks in, and providing the input as mol files might simplify the situation. But I think we were able to get around that. And thank you to all of you. The scoring and free energy results this time didn't require any reformatting. So everything was well formatted, was much easier than it was in the first Grand Challenge. So I want to start out by talking about the results of the pose prediction challenge and how things went there. So what we're looking at here is along the x-axis in this box plot, we have the structure identifier, and I've ordered these from the structure that was most consistently predicted correctly to the structure that was least consistently. So you can sort of think of this as the easy structures on the left, the more difficult structures to predict. On the right, along the y-axis, we have the RMS fit of the DOC structures to the crystal structure, and then it's colored by the scaffold class. So as you can see, the benzimidazoles seem to be, with a few exceptions, well predicted. The spiros were more difficult to predict, and the sulfonamides even more difficult. And I think, hopefully as we go down, all of us will look through these, take a look, and try to understand better. And this time I have allocated, I don't really have time to go into all the details, but I'm hoping that everyone will look at these, try to understand a little bit more about why some of these scaffold classes were easier to predict and why there were particular structures, especially within the benzimidazoles, that were more difficult to predict. So, but you can see that, all in all, it looks like there were about half of the structures that were well predicted. And in most cases, if you look at the bottom end of the box plots, you can see that in most cases, with a few exceptions over here, someone was able to predict the structure correctly within 2 angstroms. So, but right now we're looking at the distribution over all of the submissions. So let's just focus in on a few of the submissions that performed very well. So what we're looking at on this slide is actually the top 3 submissions. Now, this was sort of an arbitrary top 3. There were probably a dozen that were within statistical significance the same. So, the interesting thing about this was there were different methods used in all 3 of these with different degrees of rigor. Some people were just using the software out of the box, using default settings. In other cases, people were actually doing MD simulations to look at the poses, and then there was a lot of people actually noting that they were doing visual inspection. But I think the interesting thing about this is that as I showed you before, in about half the cases, it looks like molecules were predicted within 2 angstroms. But, again, even with this performance over here on the left side of the plot, you can see that there are still structures that were consistently mispredicted. So again, I think this is where the interesting bit lies. And really, let's try to figure out why there were these structures that were not correctly predicted. So let's move on from pose prediction and talk a little bit about the scoring components of the challenge. So what I'm showing now is a box plot comparing the Kendall tau on the y-axis for the stage 1 submissions versus the stage 2 submissions. And you can see that actually it's interesting that it appears, at least from the plot, that the stage 2 submissions performed more poorly than the stage 1 submissions. But this is actually a bit of an illusion. If we look, we can see that it was simply the fact that a lot more people submitted for stage 2 versus stage 1. So, it looks like our predictions in both cases topped out around a Kendall tau of about 0.5. Now, if we move on and take a look at free energy, this time we're going to look at the same thing, and we're going to look at the free energy submissions for stage 1 versus stage 2, and you can see that for free energy, it looks like that the median was slightly higher for stage 2 than it was for stage 1, but what we're looking at here is the notches in the box plot that indicate the statistical significance. I'm sorry, the standard deviation. So you can see that we don't really have a significant difference between stage 1 and stage 2. And the reason we've got this sort of strange looking box plot is we have a large standard deviation here. And because you have the large standard deviation that actually goes beyond the interquartile range for the box plot, you get this sort of folded in look. So let's take a look at where we are in terms of the state of the art. So again, what we're looking at here are the top 3 submissions for the free energy. And in this case, we remember for free energy, there were 2 different sets of compounds. There was a set of 15 compounds, which we'll refer to throughout this presentation as set 1, and there's a set of 18 compounds which we'll refer to as set 2. So within these sets, there were actually some very good performances. So set 1, there were 6 entries that had an RMS error of less than 1.5 kcals, and for set 2, there were 8 entries with an RMS less than 1.5 kcals. So now let's just take a look and take these two sets and compare based on the Kendall tau, the performance that we got from free energy versus scoring. And since it wasn't really possible to compare the errors for the scoring, what we're going to do is just compare the correlations. So what we're looking at here is a comparison of the Kendall taus for scoring versus free energy. So it's free energy on the left in green, scoring on the right in blue, and we're just looking at the differences here. And you can see that for set 1, actually scoring did outperform in a couple of cases the free energy, whereas in set 2, you can see if you look at the best performance that the free energy outperformed the scoring. In stage 2, where we knew the pose this time, you can see that again up at the top end we had roughly equivalent performance between free energy and scoring, but the best on set 2 for scoring was a little better than what we saw for the free energy. So, in conclusion, just as a quick wrap up, and I'm sure, as we write this up, we'll get into a lot more detail here, but if we looked at pose prediction, we had a variety of methods that performed equally well, and it seemed like it was very consistent in the molecules that were predicted well versus the ones that weren't predicted well. So about half the compounds were predicted within 2 angstroms consistently by the best methods, and the same set of molecules appear to be predicted incorrectly. So I think it'll be very interesting as everyone digs into this to understand why those molecules were poorly predicted. It was really nice to see that the free energy methods, there were multiple entries, 6 in one case, 8 in the other, that were predicting within a kcal and a half error, and a couple that predicted, with errors less than a kcal. Again, there were outliers, so we need to just dig in and try to understand the sources of the errors. Was this flexible molecules that weren't sampled? Were these force field errors? So I'm sure that people will dig into this more. And we saw that by and large, the correlations that we achieved from scoring were competitive with what we saw from the free energy calculation. So obviously it's going to be good to dig in, understand those molecules that were predicted poorly, and try to take a look at how the free energy can inform the scoring and how the scoring can inform free energy. So just wanted to acknowledge Shuai, who did a lot of the work in pulling this together, and Shuai and I working together to do this evaluation, Mike and Romy, and to all of you who've participated. Thanks.